In the deepest regions of space, light does not move through emptiness alone. It carries memory, it carries time. Every faint glow detected by our telescopes is a message from a universe long gone, traveling across expanding space for billions of years before finally reaching us. For most of human history, the earliest moments of the cosmos remained beyond our reach. We could see stars, we could see galaxies, but we could not see their beginnings. This changed when the James Webb Space Telescope was launched in December of 2021. Built through a partnership between NASA, the European Space Agency, and the Canadian Space Agency, Webb was designed to observe the universe in infrared light. This allows it to detect extremely distant objects whose light has been stretched by cosmic expansion, a phenomenon known as redshift. With this technology, Webb is able to see farther back in time than any telescope before it. Webb's mission is not only to observe space, but to observe history itself. It looks into a time when the universe was less than 5% of its current age, a time when the first galaxies ignited, a time when darkness slowly gave way to light. This era is known as cosmic dawn. What Webb has revealed is not simply an extension of what we already knew. It is a challenge to the way we thought the universe evolved. Galaxies appear earlier, they are brighter, they are more complex, and they raise profound new questions about how structure formed in the first moments after the Big Bang. One of Webb's most powerful discoveries came from its deep field surveys, including the JADES and SEERS programs. These projects were designed to observe small patches of sky for hundreds of hours, collecting faint light from objects billions of light-years away. Within these fields, astronomers identified galaxies that formed only a few 100 million years after the Big Bang. Some of these objects appear at redshifts greater than 12, meaning their light has been traveling for more than 13.5 billion years. This places them among the earliest known galaxies ever confirmed. One such system exists at a time when the universe was only about 280 million years old. Yet it already shows signs of active star formation and structured shape. Another early galaxy, observed through spectroscopy, emits radiation strong enough to ionize the surrounding hydrogen gas. This indicates that it lived during the epoch of reionization. This was the period when the first stars and galaxies transformed the opaque universe into one that could transmit light freely. Before this moment, the cosmos was filled with neutral hydrogen that blocked visible light from traveling far. What surprised astronomers was not only the age of these galaxies, but their brightness. Many appear far more luminous than models predicted. This suggests they formed stars much faster than expected, assembling mass rapidly in the early universe. These discoveries demonstrate that galaxy formation began sooner and progressed more efficiently than long-standing theories had. Before the launch of the James Webb Space Telescope, astronomers believed the earliest galaxies would appear small, faint, and irregular in shape. According to long-standing cosmological models, gravity would need billions of years to pull matter together into the large, structured systems we observe in the modern universe. However, Webb's infrared vision has revealed something entirely unexpected. Many galaxies observed only a few 100 million years after the Big Bang already showed defined cores, compact shapes, and in some cases disk-like structures. Some even resemble miniature versions of modern spiral galaxies. This discovery challenges the idea that galactic order emerged slowly over cosmic time. Instead, it suggests that the early universe was far more efficient at building structure than previously believed. Using Webb's NIRS-SPEC instrument, astronomers have analyzed the light from these ancient systems and detected the chemical fingerprints of heavy elements such as oxygen, nitrogen, and carbon. These elements are not created in the Big Bang itself. They are forged inside stars and dispersed into space through stellar explosions. Their presence in such young galaxies indicates that multiple generations of stars formed, lived, and died in a remarkably short time. This rapid chemical enrichment reveals that star formation in the early universe occurred at an intense pace. Entire galaxies may have undergone powerful bursts of activity, producing millions of stars in just a few million years. Such accelerated growth means that early galaxies evolved far faster than simulations once predicted. In some cases, these galaxies appear surprisingly massive, rivaling systems that should have taken billions of years to assemble. This raises fundamental questions about the role of dark matter, gas density, and gravitational collapse during cosmic dawn. The universe, it seems, was not slow and quiet at its birth. It was dynamic, energetic, and astonishingly productive. The discoveries made by Webb have triggered intense discussion across the global scientific community. The standard cosmological model still explains the overall expansion of the universe and the formation of large-scale structure. Yet the early appearance of massive luminous galaxies suggests that some of our assumptions about how galaxies form may need to be refined. One explanation proposes that the early universe contained much denser regions of gas than expected. These dense environments may have allowed gravity to pull material together more efficiently, igniting rapid star formation. Another possibility involves the influence of early black holes. As matter falls into these black holes, it releases enormous energy, which could make young galaxies appear brighter and more massive than they truly are. There is also growing evidence that feedback from intense radiation may have reshaped early galaxies, altering their size, brightness, and chemical composition. Such feedback processes are complex and difficult to model, especially under the extreme conditions of the early universe. Rather than disproving existing theories, Webb's data reveals their limitations. It shows that the early cosmos was far more chaotic and energetic than previously imagined. The universe did not grow quietly into its present form. It transformed rapidly, driven by forces we are only beginning to understand. Each new observation forces scientists to refine their models, improving our understanding of how matter evolved from simple particles into the vast cosmic structures we see today. The study of the universe's first galaxies is not only about understanding distant objects, it is about understanding our own cosmic origins. Every atom in your body was once created in the heart of a star. Every element heavier than hydrogen was forged through stellar processes that began in these earliest galaxies. When we observe these ancient systems, we are witnessing the first steps in a chain of events that eventually led to planets, oceans, and life itself. The first galaxies seeded the universe with the raw materials required for future generations of stars and worlds. The James Webb Space Telescope has given humanity the ability to look back to the very beginning of structure in the cosmos. It has transformed faint smudges into detailed portraits of a young universe bursting with energy and activity. With every new image, Webb pushes the boundary of what is known and what is possible. Yet despite these incredible discoveries, countless mysteries remain. How did galaxies grow so fast? What role did dark matter truly play? And what lies beyond the limits of our observation? The universe is still writing its story, and for the first time in history, we are beginning to read its opening chapters. The discoveries described in this documentary are based on verified data from the James Webb Space Telescope, a joint mission of NASA, the European Space Agency ESA, and the Canadian Space Agency CSA. All observations referenced come from peer-reviewed international research programs, including JADE's JWST Advanced Deep Extragalactic Survey, SEER's Cosmic Evolution Early Release Science Survey, NORCOM and NERSPEC instrument teams. These programs have published their findings in major scientific